Winnipeg. Shit. I'm still only in Winnipeg. Hello everyone and welcome to another video on our own devices. I'm Jean Messier and man do I ever love you guys. You guys are always sending me the neatest things to feature on this channel. Case in point, a little while ago you'll remember I made a video on the Type B Metascope, which was a type of infrared night vision device mainly used by the US Navy during the Second World War. And at the end of that video, I said that if any of you had other examples of early night vision gear floating around and wanted me to cover, then you should definitely drop me a line. Well, I asked and I certainly received because an awesome viewer who asked to remain anonymous sent me this, an AN PVS-2 Starlight scope from the Vietnam War era, one of the first modern night vision scopes ever to see combat. Now, in my Metascope video, I mentioned that near the end of the Second World War, several armies deployed small numbers of electronic night vision devices, including the American Sniper Scope and the German ZG-1229 Vampire. Now, I only briefly skipped over that topic before, and unfortunately, I'm going to have to do so again, because if I'm going to talk about Generation Zero night vision gear, I would prefer to have an actual example of it to show you on camera. So instead, I'm going to skip forward to the 1950s and cover the development of Generation 1 night vision gear like the AN PVS-2. Now, Metascopes aside, World War II era Generation 0 night vision gear was based on a type of electronic component known as an image converter tube, such as the RCA 1P25. Now, the 1P25 consisted of an evacuated glass envelope with one end painted in a thin layer of cesium and silver oxide, forming what's known as a photocathode, which, as the name implies, was negatively biased. Now, behind this was a series of accelerating and focusing anodes, which were each progressively more positively biased than the last, and then finally a phosphorescent screen. Now, when infrared radiation hit the photocathode, it released electrons via the photoelectric effect, and these electrons would then be accelerated and focused by the anodes, much in the same way that a beam of light is focused by a lens, before being projected onto the phosphor screen, which converted the electrons into a visible version of the infrared image, which could then be seen through a magnifying ocular at the other end of the tube. Now, these types of tubes operated mainly in the intermediate wavelength infrared band, which is only given off by very hot objects. So, by necessity, these were active systems. They had to be used with an infrared spotlight to illuminate target. This not only made these systems extremely bulky and heavy, but also exposed the user to significant danger if the enemy also happened to have infrared detection capability. However, in 1956, an RCA engineer named A.H. Sommer came up with a new tri-alkali photocathode composition made up of various combinations of sodium, potassium, cesium, and antimony, which was not only far more sensitive than the older cesium and silver oxide composition, but also had a broader spectral response. And this new composition, known as S20, allowed the construction of truly passive night vision devices that could gather and amplify faint sources of ambient light, such as the moon or the stars, hence why these types of detectors are also known as Starlight scopes. And the first Starlight scopes to enter US military service were the AN PVS-1 and AN PVS-2, collectively known under the rather cumbersome acronym of Surveillance, Target Acquisition, and Night Observation, or STANO. And development of these began in 1964 under the auspices of the U.S. Army Electronics Command and prime contractor Wallensack Optical Corporation of Rochester, New York, with the first units reaching troops in Vietnam starting in 1967. Right, so let's have a closer look at the scope and see how it works. Now, this particular example was surplused from U.S. government stores and refurbished for the civilian market by Tactical Night Technologies of Roseville, California, sometime in the 1990s. This comes in a nice custom-fitted metal case, which still has the US government property markings on it. And inside we have a foam liner with slots for the scope, its weapons mount, 2 batteries, and an instruction manual. So the first thing that really strikes you when you pull this out of the box is how enormous this thing is. This measures a full 18 inches or 45 centimeters long and weighs in at a whopping 6 pounds or 2.7 kilograms. So if you're mounting this on something like an M16 or an AR-15, you're going to double the weight of your weapon system. Now, starting at the front here, we have our daylight cap. This is a dark filter that protects the tube from exposure to direct sunlight. And behind this, we have our objective lens assembly. Now, just like the Type B Metascope that we looked at in the previous video, this uses a catadioptric system with a spherical mirror that gathers light and focuses onto a planar mirror, which then reflects the light back into the photocathode of the image intensifier tube. And this allows you to collect a lot of light in a fairly compact package, but at the cost of some image quality. And by twisting the barrel, you can adjust the distance focus, the objective assembly being fixed at 4 times magnification. Now, moving back, we have our 2 battery compartments, which we'll have a look at in a second. We have our on-off switch on the other side here, and then we have our weapons mount. Now, given that this is a civilian refurb, this was supplied with an aluminum mounting rail with a 1/4-20 threaded hole drilled in it, so you can actually mount this on a regular camera tripod. Now, when these were first issued, they came with mounts for a whole variety of weapons, including the M14 and M16 rifles, the M60 and M2 machine guns, the M79 grenade launcher, the M67 recoilless rifle, and even the M72 light anti-tank weapon, or LAW. Now, unfortunately, I don't have the matching adapter rail, so I've rather had to kludge this onto the rifle using zip ties, just to give you an idea of what this would have looked like in actual use. And you'll notice that the mount has its own external windage and elevation adjustment knobs, and this is because the AN PVS-2 does not have any internal reticle adjustment. You have to tilt the entire scope back and forth and side to side in order to zero it. And finally, at the rear of the scope, we have our ocular assembly, and you can adjust the focus between -4 and +4 diopters by turning this sleeve. And the eye cup is interesting since it has a pair of rubber flaps that open up when you press your eye against the eye cup and close when you pull back. And this is to prevent so-called owl eyes, the green glow from the phosphor screen, illuminating your face and giving away your position to the enemy. So now if we have a look at the battery compartment, we can see one of the other modifications that was made to this in order to adapt it to civilian use. Now, originally, these were powered by a BA1100/U 6.5 volt dry cell battery. However, these quickly became obsolete and all but unattainable on the civilian market. So what refurbishment companies like TNT did was to replace it with this little adapter that holds 4 regular AA batteries. And that just fits into the compartment like the older battery. But what about the forward battery compartment? Well, the direct predecessor of this, the AN PVS-1, was powered by a pair of 3-volt batteries. But when this was replaced by a single 6.5 volt battery in the rear compartment, the front battery was replaced by this oscillator. And this is actually what converts the 6.5 volts from the battery into the 2800 volts needed to power the image intensifier tube. Now, in the later AN PVS-2B variant, the oscillator was moved to the image intensifier tube assembly itself, and the old oscillator was replaced with what was known as ABC, or automatic brightness control, which protected the tube from being overloaded by bright sources of light. So this connects to the image intensifier tube via this little pin terminal at the bottom, and then connects to the battery via this conductive cap and a little spring clip. Now, to take apart the AN PVS-2, you first unthread this collar at the rear and pull off your ocular assembly. You then remove the oscillator. You can then slide out your MX8501 image intensifier tube. And you can see at the top the power connection pin, at the front our photocathode, and at the rear our phosphor screen. Now, unfortunately, this is a sealed unit, so I don't dare take this apart any further for fear of damaging it. But inside here are actually 3 image intensifier tubes cascaded one behind the other, so that the output of one is amplified by the one behind it. And internally, these tubes are very similar to the wartime 1P25 tube, only of course they use the new S20 trialkali photocathode material. Now, the fact that you need 3 tubes in order to achieve the desired amplification accounts for the enormous size of these early scopes. Now, normally when I cover vintage electronics on this channel, they're in too poor condition to demonstrate on camera, but today is the exception because this scope is actually in perfect working condition. So let's actually fire this up and see what we can see. So when I flip the power switch, you're going to hear that very distinctive night vision whine, and that is produced by the oscillator that supplies high voltage to the image intensifier tube. So here we have a view out of my front window at night, and here is the same view through the AN PVS-2. And although the image is a little bit grainy and has quite a bit of spherical aberration around the edges, overall this isn't half bad, especially for something designed in 1964. I can see this being very useful for picking out enemy patrols at night. Now, it doesn't appear to be showing up very well in this image, but there actually is a faint black reticle etched into the phosphor screen right in the middle of the image. Now, early versions were highly susceptible to blooming, the tube being temporarily overwhelmed by bright lights such as muzzle flashes. However, as I mentioned before, the B model introduced a form of automatic brightness control that modulated the voltage supplied to the photocathode to compensate for any rapid changes in ambient light. Now, as I mentioned earlier in the video, these scopes first started reaching troops in Vietnam in 1967, and although they were significantly lighter, handier, and more sensitive than active night vision devices such as the AN PVS-4, which was a direct descendant of the World War II era sniper scope, these scopes still had a lot of issues. For example, as I said before, they could really only be mounted on rifles since the recoil of heavy machine guns tended to shake them apart. And even then, they were really too heavy and bulky to carry out on patrol. So like their World War II predecessors, these were mainly used in a static role for defending outposts against enemy attacks at night. And even then, they were rarely used directly as weapon sights because they were so big and heavy that even the recoil of something like an M16 would quickly shake them loose on their mounts. It was almost impossible to get these to keep zero. So they were mainly used for observation and for directing the fire of other weapons. It was also very difficult to keep the electronics running in the humid conditions of Southeast Asia, while this persistent whine produced by the electronics often gave away the operator's position at night. Nonetheless, these form the basis for nearly all military night vision technology all the way to the present day. Now, the late 1960s saw the development of so-called Generation 2 image intensifier tubes, and these differed from Generation 1 in that they added an extra component called a microchannel plate between the photocathode and the phosphor screen. Now, as the name implies, the microchannel plate was a glass plate with thousands of tiny holes drilled through it. And when electrons from the photocathode struck the microchannel plate, they would bounce around inside these channels and release even more electrons via a process known as an electron avalanche. And this allowed for much greater amplification within a single tube and eliminated the need to stack several image intensifier tubes one behind the other, and allowed the production of much more compact Starlight scopes. And the first Generation 2 scope to enter US military service was the AN PVS-4, which was developed by the Optic Electronic Corporation of Dallas, Texas in 1975 and first issued in 1978. And if you're wondering what the AN PVS-3 was, this was a miniaturized version of the AN PVS-2 with a more compact objective lens assembly. Though miniaturized here is a very relative term, as this was still a very bulky scope. The AN PVS-4, by contrast, was a full 6 inches or 15 centimeters shorter than the AN PVS-2 and a full 2 pounds or 1 kilogram lighter. And while the AN PVS-2 had a rather small and useless reticle etched into the phosphor screen, the AN PVS-4 actually had an active reticle projector mounted in the middle of the objective lens assembly, and this could project a wide variety of different reticles onto the screen depending on what weapon you were mounting the scope onto. Now, the AN PVS-4 was originally fitted with a Generation 2 MX9644 image intensifier tube, though in the 1980s this was replaced by the Generation 3 MX11620. Now, Generation 3 scopes differ from Generation 2 in that they use an even more sensitive gallium arsenide-based photocathode material and also eliminate the electrostatic focusing anodes in favor of a fiber optic inverter system, which consists of a bundle of optical fibers rotated 180 degrees to flip the image right side up. And in this configuration, the AN PVS-4 proved highly successful, with over 150,000 being produced in the United States alone between 1985 and 2002, and thousands more in other countries. Now, production of the AN PVS-4 ended in 2002, and in 2003 it started being supplemented and replaced by first the AN PVS-17, and later the AN-PAS-13, which is a thermal sight that operates in the far infrared and allows the detection of human body heat and can be used over greater distances through fog and smoke. But that's getting a little bit beyond the scope of this video. So instead, to close out, I'm going to discuss some of the technical improvements that have been made to night vision scopes over the past 40 years. Now, manufacturers of civilian night vision gear will often claim that their products are Generation 4, though according to US military nomenclature, there is no such thing. All current scopes are Generation 3 with various technical enhancements added to them. For example, earlier in the video, I mentioned that the AN PVS-2B introduced a system called ABC, or automatic brightness control, which protected the tube from blooming or whiting out when exposed to bright lights. However, this only worked for overall ambient brightness and was less effective against point light sources. So later scopes introduced a similar system called bright source protection, or BSP, which modulated the voltage between the photocathode and the microchannel plate. Now, another system commonly used on modern night vision scopes is called autogating, the rapid switching on and off of the power supply. Now, this occurs so quickly that the human eye can't detect it, so you see no difference in the actual image, but it significantly reduces the overall duty cycle of the scope, that is, the total amount of time that it is switched on, thus extending its service life. Now, one of the major Achilles heels of Generation 3 image intensifier tubes is that straight positive ions from the gallium arsenide photocathode material tend to slowly wear away at the microchannel plate, potentially reducing the life of one of these scopes down to as little as 100 hours. For this reason, early Generation 3 tubes coated the microchannel plate in a thin layer of aluminum oxide to protect against ion poisoning. However, this tended to also block up to 50% of the electrons reaching the microchannel plate, greatly reducing the sensitivity of the tube. So more modern Generation 3 tubes will significantly reduce the thickness of this layer or eliminate it altogether in order to restore that sensitivity. And while this does expose the microchannel plate to ion poisoning, other developments to the overall technology have resulted in mean times to failure of around 20,000 hours, which very few night vision scopes will reach without refurbishment in the first place. Anyway, that's all I have for you today. Thank you so much for watching, and a huge shout out to the awesome viewer who sent me this thing. This is probably one of the coolest things I've ever received in the mail, and will make a fine addition to my cabinet of curiosities. Now, if any of you have other fascinating devices you would love me to cover on this channel, please drop me a line at the email below. Now, I'll see you next time in another video where we'll look at yet more fascinating night vision gear and other devices just like this one. Until then, I'm Jean Messier from Our Own Devices, and get some!